Hello everyone. Welcome to the seventh week of interaction session or tutorial session on the course on control systems. So last week, if you remember, we were discussing there was steady state error questions before, but after that we moved on to root locus, right? And we had one question of root locus, as in one question as in for the complete root locus, which comprised of many steps of questions where we did not go through all the steps because there was no concept of angle of departure because we did not have complex conjugate poles and all. So this time we are going to see different scenario as well, in which we'll have, let's say, if k varies from 0 to, or it varies from minus infinity to 0, instead of k always being positive, it could be a non-positive number as well, or if it is a positive feedback system. So what the questions that we had solved comprised only of negative feedback, right? And with k uh, always to be positive, greater than equal to 0, where we actually checked what happened, how the closed loop poles of a system move in the complex plane as k is varied from 0 to infinity. So what root locus does? I think we can go to those questions again just to get a sense of revision, and let's see what root locus is. Root locus is a graphical representation, right? It is a graphical method in control system, right? Used to show how the closed loopholes, because what we are interested in, closed loopholes. Where are the closed loopholes located? Are they lying in the left half of the S plane? Are they lying in the right half of the S plane? Is the system stable? Is the system not stable? It highly depends on what is the position of closed loopholes, right? But K can always just the parameter k can always have an effect. Maybe with the change of gain, the poles would shift, right? It might go in the, if it were stable for some values of gain k, but so what happens if I say that there is, or before that, there is some open loop system. What it is? GS is equal to CS into PS into HS, right? It is some system. Let's say it is denoted by some numerator upon some denominator. Now, if I want to see what is a characteristic equation, it is going to be 1 plus K AS by BS, right? Because when we write is equal to 0, this is the characteristic equation. I hope this is clear. Why it is the characteristic equation? Because Ys upon Rs is given by Gs upon 1 plus GSHS. Okay, and I am representing that GSHS by AS upon BS. So this is ultimately your characteristic equation. So whatever characteristic equation you get, this is for sure that this K is going to have a role in the placement of poles. Okay. So the root locus is basically a graphical representation or a graphical method in control system, which is used to show how the closed loop poles of a system. My voice is not clear. Okay. Can someone else also confirm it if it is clear or not? Not clear. Okay. I'll rejoin. I audible now clearly? Okay, thanks. Okay, so what I was saying, I was basically explaining root locus. So we know very well that root locus is a graphical representation or a graphical method which is basically used to show how the closed loop poles of a system vary if a system parameter is changed, right? That is what we do. So uh, last time, if you remember, we had done some questions for negative feedback system with positive K. Here we are going to do many other questions that would be different in a way that in some cases the gain K would be negative, it would be a non-positive number, or in other cases it would be a positive feedback system. Okay, so we are going to see all of those things. But before that, root locus is a graphical representation used to show how the closed loop poles of a system um, move in the complex S plane as system parameter is varied. My voice is, why is it not clear? Wait, I'll turn off the fan and check. Is it clear now? It's not clear? Okay. Um, Hello? Yes. I think it will be recorded also now. I hope I am clear here also. Okay. Okay, so what I was saying is, so it is a graphical method used to show how the closed loop poles of a system move in the complex plane as a system parameter is varied. In our case, the system parameter is K. Okay, so K is the gain basically in our case, which is going to uh, dominate the which is going to actually tell how the poles are going to be placed. So basically, if you are given a characteristic equation and you have some value of k over there, then the problem is that at every point of time, whenever the value of k is varying, you have to write your characteristic equation again and again, right? So with every k you have to find, okay, if my system is stable, if it is unstable, and all of that. Am I audible? Can someone just confirm once more? Okay, audible but a lot of noise. I cannot eliminate the noise. How do I do that? Is the noise gone now? Oh my god. Now there is no source of noise now in my room. Now is that clear? Am I audible? Okay, okay. Okay, so what I was saying was that with any parameter variance, I'm repeating the same thing. I've been repeating it a lot of time. But yeah, the thing is that we just want to know how are the closed loop poles located, because eventually they matter, right? That if they're placed in the right half or left half of the S-plane, are they contributing to stability or instability in the system? That is what is of importance to us, right? So when for seeing that, we use this root locus method, and I'll just go through the steps what was covered in the lecture, and then we'll go to problems. So we had a couple of questions in which this first thing that first couple of steps that I'm taking you through are for closed loop negative feedback system, and there is another condition in this case that k is greater than 0. Okay, k being a positive parameter. So I am taking you through this case first. So it's a, let us consider a closed loop negative feedback system, okay, whose characteristic equation is given by this equation, which I said 1 plus k into as upon bs. All right. So we consider the case of a causal system with k being a positive parameter. So these are the zeros of the system and these are the poles of the system, and all of them are in like in open loop case only. So it is being taken out from this open loop equation only. Okay. So the root locus traces the evolution of roots of this equation with variation in k. The root locus will have n branches and will go through the steps. Okay. So what do we do first? We first locate what are the open loop zeros and what are poles in the complex plane. So I'll take you through the example that we went through in the last class, but still you have to locate all the open loop zeros and all the open loop poles. Then you have to plot it on the uh, imaginary and real axis. So it is going to be in the S plane somewhere, whatever, wherever, whatever lies, zeros or poles. After you place them everywhere, then you have to see that you have to select test points at various places. For example, if there is a pole over here and the zero over here, and none of these exist. Okay, so you have to consider a test point over here, then in the next case over here, and the next case over here. What portion of real axis what portion of real axis does contain the root locus is defined by the number of poles and zeros that you have to the right. I'll take you to the example and all of these will be very clear, but this is how we define what portion of the real axis lies on the root locus. So for that we do this step. The second thing is we want to find out what are the number of asymptotes. So this has to be very clear that the branches emerge from the poles and they terminate at a zero. That is for sure. Okay. But since your system is of this kind, which is m less than or equal to n, that means your zeros are definitely going to be less than equal to poles, right? So if this is the case, then not if your zeros are less than equal to less than the number of equal to number equal to poles, then what is going to happen? Not all the poles branches will terminate to zero. Some of them might have to go along the asymptotes to infinity. So there comes the concept of asymptotes, and then we define what are the number of asymptotes, where do they intersect, and what are the angles at which these asymptotes are located. Then we define the breakaway and break-in point. It occurs because if there are two poles of the system and if there is a root locus emerging, let's say there are three poles and one zero. Let's say this pole terminates has a branch which terminates at this zero. Then definitely there are two other poles of the system, right? And these two other poles have to also terminate at some point. Let's say your asymptotes are along 90-degree. Then what happens? This would go this has to go along the asymptote, but it would come here, this would also come here, and since there is no zero in between, they'll have to come together and there would be a breakaway point. Break-in point means from some pole your this branch is coming and it is moving into the axis, along the axis. So we'll see those questions, but these are the breakaway and break-in points. Then there is angle of departure. So if there is a complex pole, what angle of branch it has when it is departing from there. And then we also see where does the root locus cross the imaginary axis. This is given by crossover point, and then we sketch the root locus. So before going into this lecture, because if the basics of root locus are clear to you, then I'll not go into the previous lecture, or should I go? Like I had discussed a problem with negative feedback and k greater than equal to 0. Do you want me to discuss that, or if that case is clear, if you have seen the video lecture, then I can proceed further here itself? What is that is required? There is no problem. I can definitely go to that lecture and I'll show you what is going on. Just let me know if you need it. If you don't, then I'll proceed here. Okay, I'll go through the last lecture and then I'll continue. So it was in week 6. Okay, so what we had done here was the following. If I say the similar steps, then you can see here that there was a closed loop or an open loop transfer function defined with a negative feedback closed loop system, and this closed loop system had a case where it was non-negative real valued parameter. K was non-negative, that means K was greater than 0. This was the first case. Second case is that it is a negative feedback closed loop system, right? Since it is a negative feedback closed loop system and this case is being applied of K greater than 0, that means that both of them together will imply that we'll have to follow the steps of the first procedure. Now, if we want to know for this, so this is a third order system, right? K upon S cube plus 4S square plus 8S. From here, if you take out S to be common, then you'll get 3 poles. S is equal to 0 and 2, which would come from the quadratic equation. So from here, we have to define what is the number of branch. Now, the number of branches is defined by how many poles do we have. We have 3 poles and we have 0 zeros. That means three branches would emerge from the poles, right? But they won't terminate at 0. Like it would emerge from some 3 poles and it would go to 0, but those zeros, uh, since we do not have any 0 here, so it would go along the asymptote and would go to infinity, right? So in this case we have number of branches to be 3, that is given by n, which is the number of poles, and the number of branches that terminate at open loop 0 is 0. That means the number of asymptotes would be given by n minus m, which is 3. But make this very clear in your head that every pole, from every pole, a branch is going to originate and it is going to terminate at 0. This is for sure. Okay. Now, if your branches emerge from the poles and then they terminate at some 0, but if 0 is not present, then where would the branches go? They have to go along the asymptote to infinity. Okay, and for so that is why this formula is used, n minus m. If zeros are there, definitely some of the branches will terminate to 0. If zeros are not there, they are going to go to infinity along the asymptotes. Okay. Now, if you see the 2 poles which I said are given over here, what was the next question? The region of the real axis that
Hello,
drives.
ma'am.
Sorry.
Ma'am. Hello,
Yes.
ma'am. Sometimes open loop system equation will be given. I mean transfer function. In that case, we need to formulate closed loop system, and then we have to continue root locus.
No, you have to work with the transfer function of open loop system only. For example, uh, see, this is the open loop transfer function, which is given by this transfer function. It is not closed loop. Closed loop would be this upon 1 plus gs hs, where hs is 1. So what we are doing is, if you take into account the complete characteristic equation for closed loop system, you will not get a transfer function of this format. So it is essentially dealing with the open loop transfer function and seeing how the closed loop poles vary with respect to k.
Oh, okay.
Okay, then in this case we had seen that what region on the real axis lies on the root locus. So you identify what are the poles of the system. So the ones marked in red are the poles of the system. It is at 0, it is at minus 2 plus 2j, minus 2 plus 2j, and minus 2 minus 2j. Okay, these three are the poles of the system. Now, after this, I'll write in some other color, yellow. We'll take a test point over here at ST and we'll see how many poles or zeros lie on the real axis to the right of it. In this case, it is 0. So if it is 0, that means it is not odd. If it is not odd, we discard this region. Then we move to the next region, which maybe lies here. Okay. We check what is the number of poles and zeros to the right of it on the real axis. Here we get it to be equal to 1. That means it is like how if the number of poles or zeros that you have on the real axis to the right of the test point is odd, then that region lies on the root locus. Okay, that is what we were discussing in that point also, that if towards the right there are odd number of zeros and poles in together, then we have that region lying on the root locus. So if the question comes, what is the region on the real axis that lies on the root locus, this is the correct answer. Okay, then after this we were to find what is the number of asymptotes. It is definitely n minus m, and it is given by 3 minus 0, which is equal to 3. Okay, then the next case is the angles made by the asymptote is what? The formula for angle is given by this, plus minus 180 degree 2k plus 1 by 3. Okay, so what we do here, we insert the value of k, 0, 1, 2, 3. You can go in negative also, you can go in positive also. If you go clockwise, then it would become negative, but it is eventually positive only if you consider from the other direction. So you can always put the value of 0, 1, 2 here, and you put, you'll see that it is 60, 180 and 300 degrees. Okay, now so all of these are very intuitive things. If there are asymptotes, the asymptotes will be placed in such a way that you complete 360-degree angle. The kind of placement you have is in this way, because you see it is just division of 180 degree into how many you need by the number of asymptotes. Okay, so all of these are the angles at which the asymptotes would go. And the next question that we had was, where do they intersect? The intersection is given by sum of poles minus sum of zeros upon n minus m. So this gives us the intersection of asymptotes. So what is the sum of the open loop poles that you've got minus the sum of open loop zeros that you have divided by n minus m. Okay. And then we wanted to check what is breakaway or break-in point. It is given by a certain formula in which you have to find this a dash s into bs upon minus b dash s into s, where this gs hs whatever you had k upon s cube plus 4s square plus 8s is only as upon bs. So differentiating that, this formula is derived, and from here you just have to substitute the values and check what is the value of k that you are getting. If the value of k that you have from the value of s derived is not real, or it is, if you had started for k greater than 0 but it turns out to be k less than 0, then all of those are problem, and then you find if there is a breakaway or break-in point. Okay, and for this diagram, for this particular diagram, the root locus was of this kind, where there were three asymptotes. Okay, the 1, 2 and 3, these three were the asymptotes, and the root locus moved along them. Okay, so we'll see today's question now. Before that, just to reiterate, I'll go through these points one again. So what you do, what is the first step you do? You locate all the open loop zeros and poles, okay, in the complex plane, and then you see that which part of the root locus lies on the real axis. So you just have to check the number of open loop zeros and poles that are lying to the right of it are even or odd. If they are odd, then that portion lies on the root locus. Third point is you want to find out how many asymptotes will be there. The number of asymptotes is given by n minus m. The other thing is you want to find out what are the angle of these asymptotes. That is given by this formula. The other thing is you want to find out the point of intersection of these asymptotes. So this is not minus sign, this is just equal to sign. So it is given by sum of the open loop poles minus sum of open loop zeros upon n minus m. Okay, so this formula. Okay, after this we want to check what is the breakaway or break-in point. Breakaway or break-in points occur when there are two poles lying together and both of them have branches emerging. Both of them break away from here. If they are coming back, then both of them break in here and move in the opposite direction. So that is why there is breakaway or break-in point. So after solving this equation, you basically, this is the most important equation. After solving this equation, you basically get to know if there is a breakaway point or break-in point present in the system or not. And then you locate the angle of departure. Angle of departure is angle of departure or angle of arrival. If it is coming getting out from a pole, it is angle of departure. If it is coming to a zero, then it is angle of arrival for that zeros. Okay, so it is the angle of departure from an open loop complex pole is 180 degree minus sum of the angles made by the vectors from the other open loop poles to this pole plus sum of the angles made by vectors from open loop zeros to this pole. We'll go through this. We have the question there, but this is basically to know that at what angle it is either departing from the pole or arriving at a zero. Then we also want to know what are the points where the root locus may cross the imaginary axis, because that is of importance. If it crosses the imaginary axis and moves to the right of the s-plane, we know that for those values of k, the root locus is going to be unstable. The system is going to be unstable for those values of gains. So we need to know what is a crossover point beyond which we cannot uh, make the gain k of that value, because it might make the system or destabilize the system. Okay, then we sketch the root locus. Now this was the condition, all of this were these were, and another thing is, since we are dealing with polynomials with real coefficients, the root locus will be symmetrical with respect to the real axis always. All of these conditions that we read was for negative feedback system, right? And the other thing is for k greater than 0. But what would happen if there are other cases? Let's say if there is a case of positive feedback system and k greater than 0, or there is a case of negative feedback system but k is less than 0. So for these two cases, we follow a different. So you see, there has to be one difference only from these set of rules. It was negative feedback and k to be positive. Now, if any one of the thing changes, here it is a positive feedback and k is greater than 0. Or if it is the same negative feedback but k is less than 0. If one of the things changes, then there are some changes in the rules that we have to observe. Okay, the most important rule that we need to see is the test point one, where we wanted to locate where is the root locus lying on the real axis. So we used to find a test point, right? And in this earlier cases, what we said, if there is a test point, then the number of poles or the number of zeros that you have on the real axis, if you add all of them, should be odd to the right of test point, then that region lies on the root locus. But or root locus lies on that region. But here in this case, we just change that to even. It is not odd. If the number of open loop poles and open loop zeros lying on the real axis to the right of the test point is even, then that point lies on that region lies on the root locus. Okay, so this thing only changes, and here one formula changes, which becomes 360 degree instead of uh, 180 degrees, and here instead of 180 degree we have 0 degree coming over here. Okay, these are the only differences. So I think this document is already accessible to all of you, uh, because we will be referring to it time and again now. Okay, let's start. um, so the first question is, let the open loop transfer function of a negative feedback closed loop system be given by this, where k is a non-positive real parameter. You see, the exception has come here. Here our k became less than 0, less than equal to 0. And it is a negative feedback system. That means we have got this one change. We have this case coming up. Okay. So consider the locus of the corresponding closed loop poles. The region of the real axis that lies on the root locus is what? Okay, that is what we are supposed to define. So what is a region that is, so for this what we have to do first, let's identify what are the zeros and poles of this open loop transfer function. So for poles, it's going to be s into s square plus 2s plus 5 is equal to 0. From here you get s to be equal to 0 or s to be equal to minus 1 plus minus 2j, right? These three are the poles of the system. Let's draw it. So this is the pole of the system, which is s is equal to 0, and the other pole is minus 1 plus 2j minus 1 minus 2j. So this is minus, this is 2j, this is minus 2j, and this is minus 1. Okay, these are the poles of the system. Now what we have to do, how many regions do we check, do we need to check? We need to check, so we have to look what are the poles and zeros lying on the real axis. There is no zero, right? Because in the numerator we don't have any s term. So there is no zero. There are only poles. There are three poles. But how many of them lie on the real axis? Just one pole, which is s is equal to 0, lies on the real axis. So it divides the real axis into two parts. One is this part and one is this part. So we have to check which of them is uh, going to lie on the root locus is going to lie in which of these regions. Okay, so let's take a test point. Let's take a test point here. Okay, now the number of poles and zeros to the right of this test point should be even. We have zero number of poles and zeros to the right of this test point. Okay, that means this region is going to lie on the root locus. The root locus is going to lie on this region. Now let's check, have a test point here. The number of poles and zeros to the right of it is 1. Be mindful of what you are counting. You don't have to count this. You don't have to count this. You have to count the number of poles and zeros that are lying on the real axis. Once you count, you get it to be equal to 1, so it becomes odd, and hence this does not lie on there is no root locus lying over here. Okay. So from here you can say that 0 to infinity is the region of the real axis that lies on the root locus. All right. Let's move to the next question. In the problem 1, which one of the following statements is true about the locus of the closed loop poles? So how many poles were there? There were 3. How many zeros were there? 0. So what is the number of asymptotes? Because there are no zeros present over here, so the poles, the branches emerging from the poles would not terminate at some zero, rather it would go along the asymptotes to infinity. So your number of asymptotes is given by n minus m, which is 3 minus 0 is equal to 3. Okay, so it would have 3 asymptotes. The other question is, the other option is, it would have the positive real axis as the one asymptote. It would have the negative real axis as as the only asymptote. No, because we have 3 asymptotes, so this only word is definitely problematic. It would have both the positive real axis and negative as asymptotes. Okay, so let's see what is the asymptote. We should definitely check, apart from the number, at what angle they are moving. Okay, so, and as I said, the asymptotes always cover the entire range. So if it is 0 and 180 degree, you're done. You can have just two asymptotes, but we need three. So it has to be symmetrically, the three have to be equally divided in the 4-quarter region. So let's check what is the number of asymptotes. Okay, sorry. Okay, so after this, first let's check what is the point of intersection of these asymptotes. Okay, so the point of intersection is given by sum of open loop poles. What were the poles? They were 0, minus 1 plus 2j, minus 1 minus 2j. It's going to be 0 plus minus 1 plus 2j plus minus 1 minus 2j minus 0, because there are no zeros, upon 3. Going to be minus 2 by 3. So this is the point of intersection of these three asymptotes. Okay. Now after this, let's check what is the angle of intersection. It is given by plus minus k into 360 degree by 3. Right? This is what is given here. And k varies from 0, 1, 2 and so on. So let's have the values. Let's put k is equal to 0. It becomes 0. Let's put k to be 1. Then it would be plus 360 by 3 and minus 360 by 3, which means plus minus 120 degrees. These three are the angles of asymptotes, right? So this is also incorrect because it won't have any asymptote along the positive real axis and negative real axis. Okay, so your answer is A, that it would have three asymptotes. Okay, let's move to the next question. In the same problem, which one of the following statements is true about the locus of closed loop poles? We are talking about breakaway and break-in point, right? So in this case, your characteristic equation, just let me write the question once again. Your AS upon BS, actually KS upon KBS is given by K upon S cube plus 2S square plus 5S, right? Now, for characteristic equation, it is 1 plus K AS upon BS is equal to 0. And your K is less than equal to 0, right? We already saw this. So from here, we need to find out what is A dashes and what is B dashes. Okay, so if you find A dashes, you will directly see that it is 0. K card division, K upon ds is 0, dk upon ds, because K is a constant. For B dashes, it would be 3s square plus 4s plus 5, right? So after this, what we have to do? We have to find B dashes into AS minus BS into A dash S is equal to 0. Substitute the values. You will get it 3s square plus 4s plus 5 into K. Right? Is equal to 0. Now, K is 0 or 3s square plus 4s plus 5 is equal to 0. From here, if you try to find out what are the roots of this equation, you'll get them to be minus 4 plus minus 16 minus 4ac. That means 4 3 are 12 and 12 5 are 60 upon 2a, which is 6. From here you can see that you'll get complex poles. Now from here it is very clear. If there are complex poles, obviously breakaway and break-in point has to lie on the real axis, because your root either breaks away from here or breaks in here. If it is complex pole which is coming over here, when you want to find out what is the breakaway or break-in point, it does not exist. The answer is definitely not valid. So these are the complex poles and they cannot be breakaway or break-in point. So the correct answer is it neither has a breakaway point nor a break-in point. Okay. I hope this is clear. Okay. Let's move to the next question if there is no confusion. Then for the same problem we want to define what is the angle of departure. I hope all of you have the sheet that I shared, the steps to construct root locus. It was shared in the NPTEL, where the place where you have all the, like, there is a column where you have all the uh, week wise lectures uploaded, and there you have assignments coming and everything. In the same place there is a document attached in week 6, which is steps to construct the root locus. I have just referred to the same document, nothing from outside, so kindly use it. Okay. So now we want to find out what is the angle of departure of the root locus branch from the open loop. So we have a pole which is a complex pole. So there is definitely some branch which is going to come out of from there. Now if some branch is going to come out from there, it would be along some line like this. So what is the angle of departure for this pole? That is a question that is being asked. Okay. So let me plot this properly. There is a one pole at 0, -1 plus 2j, and -1 minus 2j. Okay. Now what we'll do, we'll see what is the angle made by the vector. Just let me get back to this. What is angle of departure from an open loop pole? The angle of departure from an open loop complex pole is given by 0 degree minus sum of angles made by the vectors from other open loop poles to this pole. Matlab, if let's say this pole is in question, then what is we have to find 0 minus sum of the angles that would be made by other open loop poles to this pole. If there is a, so what is this angle which is being made? Then what if there is a pole over here, what is the angle which is being made to this pole? All right. Plus the sum of angles made by vectors from open loop 0 to this pole. Okay, so it is 0 minus sum of the angles from the open loop poles plus sum of the angles made by 0 from the open loop zeros. Okay, so let's see. Okay, so angle made by the vector from 0 to -1 plus 2j is what? It is 90 degree. This angle is 90 degree plus, what is this angle? It's tan inverse, this complete is 1 and this is 2. Tan inverse 1 by 2. So it's going to be 90 degree plus tan inverse 1 by 2. You will get it to be around 26.56 degrees approximately. Okay. So this is the angle that you have from here. Now let's check for this pole, that what is the angle this pole is making with -1 plus 2j. Angle made by the vector from -1 minus 2j to -1 plus 2j. It is 90 degree, right? So after this, we have to find what is the angle of departure. It is given by 0 degree minus sum of open loop poles, sum of the angles made by open loop poles, (90° plus 26.56 degrees. So, okay, 0 degree minus this plus this. So it's going to be this 90°. Okay. So from here what you'll get, it would be equal to 90, 90, 180 and 180 plus 26.56. What does that mean? It is minus 206.56 degrees. Okay. If you take out the equivalent, you can subtract it from 360°. You'll get it to be around 153.43 degrees. Okay. So what it says is the angle of departure from this pole, the angle of departure from this pole is at 153 degrees. So from here it is 90. Now from here it would go at 150 degree. This is the angle of departure from this pole. Okay, and it is along which asymptote? It is along 120 degrees. It departs from here along 120-degree asymptote. So we'll see at the end what is the root locus. But this is how you find angle of departure. Okay. Now after this, the closed loop system is stable for what values of k? So what was our region on which we were drawing everything? The as the region uh, 0 to infinity, which was our region on which root locus would lie. Okay, lies on root locus for all values of k less than equal to 0, the system is unstable. We just have a pole over here, and this is the only region. Okay, so the system is unstable. Let's see the root locus, which is important. So yeah, you can see this is the root locus. So this is your 0-degree line. This is your this is the point of intersection of asymptote. What was it? We had derived it, right? It was minus 2/3. go along this line. So it departs at 153-degree angle from here, and it goes along this asymptote, it goes along this asymptote. So that is why this is the root locus. And the one from s is equal to 0 goes along 0-degree line. So these three are the asymptotes, and this is how the root locus is moving. Okay, and at the poles it is k is equal to 0. As you move along the asymptote, you reach k is equal to infinity. Here also k is equal to infinity, k is equal to infinity. So when the previous question was asked that the system is stable for what, for what value of k, so you can see that for this pole, as k is uh, as k moves from 0 to infinity, or it would be minus infinity to 0, whatever, but we plot it in such a way that we can write k is equal to 0 to infinity. You can see as we move along, as we move from k is equal to infinity, it always moves in the right half of the s-plane. So this pole, irrespective of these poles being in the left half of the s-plane always, this pole which is at s is equal to 0 is going to cause instability in the system for any value of k. So this system is forever going to remain unstable. So your correct answer is no value for k less than 0. Okay.
When it is given stable for
Yes.
whose
It is
loop
stable
system
for.
is stable for
So it is not
minus
stable
2.
for any value of k, na, because we are in this right half of the s plane forever. Got it? Matlab, see, we are always in the right half of this s plane for k value for corresponding to s is equal to 0. So as we move along increasing the value of k for 0 to infinity, which is taken here by the process we take here, which is minus 0 to minus infinity to 0. So there is no value
Now
of
the
k.
question, ma'am,
Yeah.
in the question it is given the problem is stable for, and k for less than 0, that is negative, it is unstable, known.
Mm-hmm.
How can you make it stable? Is stable for what value of k means uh, uh, most everything is almost negative only. If it is in right of S plane, it is unstable. But in the
Mm-hmm.
question closed loop system problem only stable for what value? If the question itself is saying stable,
Hmm.
is it talking about making this system stable?
No, it is not asking you to make the system stable. It is asking you that given this is the system and given that your k is always negative, so is there some value of k in that range minus infinity to 0 which for which the system is stable? So when we move in this region vary our k from 0 to infinity, we see that for none of the values of k we get the system to be stable. It is always unstable because of our closed loop was very negative.
Okay.
Okay, let's move to the next question. This is a question which in which it is just said that if it were a positive feedback system with everything remaining the same, which means your k is less than equal to 0 plus it is positive feedback. That means what? If you, if I change the way of thinking, I can say, I can make it equivalent to k greater than equal to 0 and negative feedback system, right? Because what happens if your open loop transfer function GSHS is given by KAS upon BS, then my closed loop transfer function is YS upon RS is KAS upon sorry, as upon bs, which is gs. uh, I should not take hs here. Hs is 1. Okay, 1 plus k as upon ps. So if I, in my case, it is k less than 0 and positive feedback, which means it is 1 minus k as upon bs. What if I invert the sign of ks and say k is greater than 0? Okay, then I'll have to invert this sign also. So this becomes negative feedback with k greater than equal to 0. So this is our original case, the first case that we saw, in which we had um, uh, for checking, placing the test point and checking that if the number of poles and zeros to the right of it on the real axis is odd. So we are back to that question. Okay. So if one had positive feedback in problem 1 with everything else remaining the same, which of these statements would be true? So the locus of the closed loop poles would have only one asymptote, it is saying. No, it would have three asymptotes only, right? Because n minus m is universal. Number of asymptotes is n minus m, which is 3 minus 0 is equal to 3. So this is wrong. Okay. All the branches of the locus of the closed loop poles would lie in the left half of the S-plane for finite range of k. Let's check this. So uh, okay, so all the branches of the locus of closed loop pole would lie in the left half of the S-plane for finite range of k. This is what it is asking. So let's find what we'll have to start the process again. So what is a part on real axis? So if there was one pole at 0 and two complex conjugates, then when we saw, we want to have negative. So this is the region, right? Minus infinity to 0 is the region. So minus infinity to 0 is the region for which we want to talk. Okay. Now we want to check all the branches if they would forever lie in the left half of the complex plane or not. What should we do for checking that? Because we want to see if the root locus forever lies in the left half of the S-plane, we have to check if it ever crosses the imaginary axis. Okay, we know from here that it is lying over here. The root locus will lie on this part of the real axis, but we should also make sure if it is going to uh, have a crossover point, if it is going to cross the imaginary axis and go to the right half of the S-plane. If that is the case, then only we can comment on the second statement. Okay, so for that what we'll do, we'll find out what is the crossover point. If we find out the crossover points, so if you find out the asymptotes and everything, you'll get, in this way only you'll get minus 180-degree multiples and all. So let's check crossover points first, because that would give us a hint where it lies. If it ever moves to the imaginary axis, if we get a point on the imaginary axis which it is crossing, that means it is bound to go in the right half of the S-plane and destabilize the system. So for crossover point, what we'll do, we'll just substitute S with just j omega, because there is no real part and only complex part is there on this imaginary axis. Okay, so it would be 1 upon, let's assume some k hat, because we want to find out what is the value of k hat or what is the value of S for which it is crossing. K hat upon S cube plus 2s square plus 5s is equal to 0. From here you can get, let's substitute omega, minus omega cube j plus no, minus 2 omega square plus 5j omega plus k hat to be equal to 0. The separate the real part and the imaginary part. So it's 2 omega square k hat minus 2 omega square plus, after this it is 5 omega minus omega cube into j is equal to 0. Okay, so for this whole term to be 0, both of the real parts and imaginary parts have to be 0 independently, right? So if they have to be 0 independently, that means k hat is equal to 2 omega square and omega into 5 minus omega square has to be equal to 0. So from here you can see, well, let's solve this part first. So omega into, so either omega is 0 or omega is equal to plus minus root 5. Okay. Now for omega equal to plus minus root 5, k hat is equal to 10, right? If you substitute this here. For omega is equal to 0, k hat is equal to 0, which does not give any hint, but for, because it is coinciding with the pole, but for k hat is equal, for omega is equal to under root plus minus root 5, k hat is equal to 10, which is greater than 0, right? And we were solving for question which has k greater than 0 and it is a negative feedback system. That is how we attempted the question, right? So this condition of k being greater than equal to 0 is satisfied here, which means there is a crossover point. Okay, so thus the two branches starting from complex conjugate poles will cross the imaginary axis to RHP, right half of the S-plane, as k hat tends to infinity. So from here we can say that all the branches of the locus of closed loop poles would lie in the left half of the S-plane for finite value of k. This is not correct, right? If it is saying for a finite range of k, that means for some value of k it is going to lie in the left half of the S-plane. Because just a second, let me check the answer to this question. This is question number 6. Yes, they say the second option to be the correct option. So this finite word, it is talking about only some range of k. So all the branches of the locus of closed loop poles would lie in the left half of the S-plane for finite range of k. For some range of k, it is going to lie in the left half of the S-plane.
Thus k greater than 0 but k within 10. Yeah,
Right. Not within 10. cannot say k within 10. We don't know if it is the bound.
A value and j omega is substituted.
I mean, this is the particular k value for crossing the imaginary axis. So if there are poles over here and here, and if they are crossing the imaginary axis, here k hat is 10 and here k hat is 10. If they move beyond this, then it is going to cause instability, right? K has to be within 10. That's right. If k hat is within the range of 0 to 10, that means it is going to lie in the left of the S plane. That's true. Okay. Third option is the closed loop system would be stable for k less than 0, which is not true because we want to have k to be greater than 10. And the fourth option is the locus of the closed loop poles will have one breakaway point. Now this breakaway point would follow the same analysis, right? The one which we used earlier. Where did it go? Yes, this analysis.
There is no breakaway.
Yeah. Because ultimately we are going to use this equation only, kas upon ps, and from here we are going to get the same answer. So there is no breakaway point, so B is the correct answer. Okay, for this, so this is the root locus that you can see later, but along this asymptote, this root locus moves here. This is again k hat is equal to 10, and it moves in this direction along the asymptote, and from here you have this asymptote, and this is the intersection point of the asymptotes. So this is the root locus that we get from here. Okay. Okay. This is again the repetition. I want to go into this. Let's move to the next question. Question number 7 says, this is again a new transfer function on which we will have the further questions. The open loop transfer function of a positive feedback closed loop system is given by this equation, where we have 1, 0 also coming now into picture, and there are two poles where k is a non-negative real valued parameter. Consider the corresponding locus of closed loop poles. Which of the following statement is true? Okay. So let's see where are the things lying on the imaginary axis. So here is 2, which is an open loop 0. Then we want to see what other poles are there. Open loop 0 is at s is equal to 2. Open loop pole is at s is equal to it would be a -3 and -1, right? So we have two poles at -1 and -3. From here, it is very, very, very evident that if two poles are coming together, definitely there is going to be some breakaway point. Some branch is going to emerge from this pole, both of these poles, and then they are going to have a breakaway point, and they are going to move in two different directions. Those directions also we don't need to guess what it would be, because the number of asymptotes would be too
Ma'am, here he is asking positive feedback, ma'am.
sorry.
Telling positive feedback and K is of course positive.
Yes, positive feedback and k is also positive.
K is positive.
So that means we are in the second case.
That is to the right of that it should be even.
Right. So from here, initially you can get intuition of what root locus could be, but let's now move step by step. Since the question asked which of the following statement is true for region lying on the root locus, let's move to that. So if I have a test point here, the number of poles and zeros lying to the right of it is 0, which means this region would be there 2 to infinity. For this region it won't be there because the number of poles and zeros to the right of it is uh, odd. Then again for this region it would be there, for this region it won't be there. So the regions that are lying on the root locus is -3 to -1 and 2 to infinity. We don't have 2 to infinity in the option, so -3 to -1 is the correct option. Okay, let's move to the next question. In the same problem, which of the following statements is true about the locus of closed loop poles? So it's asking about number of asymptotes first, which is given by n minus m. N is 2, m is 1. So there would be just one asymptote over here. Okay, what would be the angle of this asymptote? It would be plus minus 360 degree by n minus m, which is 2 minus 1. So it's gonna be 0 degree, you can say directly, right? And point of intersection, since there is only one asymptote, we don't need to see the point of intersection, but still let's see what happens if we put this in general formula. Point of intersection is -3 minus 1 minus 2 upon 1. What does that mean? It means
Plus 2. 0 is plus
no,
2.
minus 2. It is -6, right?
Numerator 0 is minus 2. 0 is s is equal to 2, madam. Minus of minus 2 is plus.
No, no, no. S is equal to 2.
Ah, minus of minus 2. Okay.
This 0 is
Minus 2.
negative over here, so it would be 2 only. This is -6. So what is happening? We are getting arbitrary number over here. But we already know that the angle of asymptote is 0 degree. So there is no point of finding out the intersection. So what that means is complete real positive axis. We can say that real axis is the asymptote at 0 degree. That means this line would be the asymptote along this line. Okay, so from here the questions are, it's asking positive or negative real axis also. -4 minus 2 upon 1, which comes to be -6. Any idea how do we how can we say if it is positive real axis or negative real axis? Because the first two options are definitely incorrect. It does not have two asymptote, it does not have any asymptote, both of them are wrong. It has one asymptote and it is along some axis. Then how do we say it is positive in the real axis or negative real axis? Since
these two poles has to branch, and one should unite with the zero,
right,
and that has to come from, because this real axis is not a point, it has to come from other side
right,
clockwise,
right.
and one more will go to infinity. So
Right.
it's going to be
So if we
positive real
see the
axis.
whole picture, we get an idea that okay, this has to be positive real axis. But if I
Yes.
don't move to that step and I check here, is there something which comes out from the formula that helps us notice it? Or just saying that angle of asymptote is 0 degree because it is along this direction should mean that positive real axis is the asymptote. Because the only way I find without looking at the complex root locus picture that how everything should be arranged when it should be moving from pole to zero, and my poles are on the left half of the S plane, my zero is in the right of the S plane, and it should terminate there, and we should have it along the positive real axis as the asymptote. But I see this 0 degree should help us.
Yes, yes, ma'am.
Zero degree positive real axis. Okay, then let's move to the next question. Where is the break in point? Okay, again we have to solve this. From here we have to find 1 minus k, it was s minus 2 upon s square plus 4s plus 3 is equal to 0. Okay, from here if we try to find out what is a dash s, it's going to be 1. B dash s is going to be 2s plus 4. Thus b dash s into as minus bs into a dash s is equal to 0. So b dash s is 2s plus 4 into as is s minus 2 minus bs is s square plus 4s plus 3 into a dash s is 1 is equal to 0. If we simplify this, it would be 2s square minus s square plus 4s minus 4s minus 4s, so it should be minus 4s, and here it would be minus 8 minus 3 minus 11 is equal to 0. From here if you find out the values of the roots, what do you get?
5.87 minus 1.87.
Okay, 5.87 and minus 1.87. So from here, unlike the last question, we are getting the points on the real axis. That means they are potential break-in points or breakaway points. They are for sure, they might be because they are not complex right now. They are some values which are lying on the real axis. Now our duty is, our next duty is to check if uh, for, if they satisfy the value of k for which we are working. Like we are working for k greater than 0 in this question. We are working for positive feedback at k greater than equal to 0. So for the same values of k, we should definitely get k greater than 0, else we won't solve the question. So firstly, let's go with k is equal to 5.87. So k is equal to, from here we can find the value of k in the following way. This itself will give you the value of k. You take the value of k to be on the other side and just invert the numerator and denominator. So it's just k square plus 4s plus 3 upon s minus 2 From here, when you substitute the value of S to be 5.87, you should get K to be equal to 14.7, which is greater than 0. That means this value of K is greater than 0, and hence it is either a breakaway point or breaking point. We'll discuss what it is. Now let's check for second value. For S is equal to minus 1.87, and from here if you substitute it here, you get it to be equal to minus 1.87. Sorry, for breaking point also 0.254, which is also greater than 0. That means this is also either a breakaway point or a breaking point. That's what it is. Now let's be clear on what is a breakaway point and what is a breaking point. So how do we classify? So we know already what are the positions. Our 0 is at 2. At minus 1 we have 1 pole, and at minus 2 we have another pole, right? If can you please mute yourself? Thank you. So this is a 0, and this is a pole over here which is minus 1 and minus 3. Definitely there are two points, right? So I'll change the color of my pen. One of them is 5.87, which is some point over here. One point is minus 1.87, which is somewhere here. So definitely if it is lying in between two poles, it is going to be a breakaway point. That means this minus 1.87 is a breakaway point. Because from nowhere we had the hint if this is a breakaway point or break-in point. But after seeing where it is lying, since it is lying in between two consecutive poles, it has to be a breakaway point. The other point is here at 5.87. It is not lying in between consecutive poles or consecutive 0. So this is definitely a break-in point. And both of them are valid because we've got valid values of K for both of them. So this is a break-in point.
But ma'am, it's chosen as positive feedback. As you said, to the right of that test point, if I take it, it should be even, and that is also valid now. It should be a test point. If I take it as a test point there, and to the right of that we have the even number of poles plus zeros.
Right.
So that it's a valid one,
Yeah. So
valid breaking point.
this region is lying on the root locus, and this region is also lying on the root locus. This we already did, that which of the root locus lies in which region, and this was the region and this was the region, and in those regions only we are getting break-in and breakaway point. So that's right, you get another validation from here. Is this the thing that you were asking or something else?
It has to be a root locus point in the positive side of the axis, because to the right of that on the real axis we have even number of poles plus zeros.
Hmm.
So according to, if it's a positive feedback as you told, it must be a point number. It must be a breaking point problem.
Right. So there is no confusion, right? You agree with what we are
Yes.
saying?
Yeah, that's fine. That's fine.
Okay. So yeah, this gives a good validation that since both of these were the only regions which were lying on the root locus, so if we get a breakaway or break-in point here, that says that yes, we have got the correct points. One more thing is you validate it and check if the value of K that you're getting does match with the calculations that we had started. So for K greater than 0, both of these are valid, and hence both of these are breakaway or break-in point. If had we got for S some complex value, it would not have been a breakaway or break-in point. Or if we had the value of K to be negative coming out from those values of roots, then also It would not have been a breakaway or break-in point, but in this case it is. Okay, so next question is the value of k at the break-in point. The value of k at the break-in point is what? We already calculated. At break-in point it is 15.74. It is just substituting the values, 15.74. And for breakaway, what was the value? It was 0.254. So the breakaway point was at minus 1.87 and 0.254 was the value of k at that point. Okay. So where are the crossover points for the same root locus? So let's put it in the characteristic equation and then find out what is the value of omega and k that we get from here. So for crossover points, s is equal to j omega. Put s is equal to j omega in the closed loop characteristic equation. So it is 1 minus k. Since it why we are putting minus here? Because it is a positive feedback system. S square plus 4s plus 3 is equal to 0. So s square plus 4s plus 3 minus k s minus 2 is equal to 0 at s is equal to j omega. We have to check. So it's going to be minus omega square plus 4j omega plus 3 minus k j omega minus 2 is equal to 0. If we just separate the real and imaginary part, but 2k minus omega square plus 3 plus j 4 omega minus k omega is equal to 0. From here, so this is a function of both k and omega. We will not touch that first. From here we'll try to find out what is the value of omega and then substitute here. So from here either 4 minus k is equal to 0 or omega is equal to 0. Okay, these two are the conditions for either k is equal to 4 or omega is equal to 0. For omega is equal to 0, we'll substitute here. It would be 2k plus 3 is equal to 0. So from here, k is equal to minus 3 by 2. But k was greater than equal to 0. So this does not hold true. Okay, let's check for k is equal to 4. For k is equal to 4, 8 minus omega square plus 3 is equal to 0. From here we can write omega is equal to plus minus root 11. From you'll get it to be equal to plus minus 3.32. So s is equal to plus minus j 3.32 is the crossover point at k is equal to 4. I hope this is clear. It is just finding out where are the crossover points, because definitely there is a 0 in the right half of the S-plane and there are 2 poles in the left half of the S-plane. The branch has to go from pole to the 0. So it is very definite that there is going to be crossover point. Since the root locus is going to be symmetric about real axis, we'll have another crossover point coming into picture which would go along the asymptote. Okay, and since we have the asymptote to be 0 degree, which is the positive real axis, so definitely the other pole also has to have a crossover point to cross the imaginary axis and then go along the asymptote, which is along 0 degree, and the other pole has to terminate at 0. And where are they going to meet? They are going to meet at 2 points. One is breakaway point, one is break-in point. So these two poles are definitely going to break away from here. They are going to have a crossover point here, at 3.32j and minus 3.32j, and here there is your 0 at 2. They are going to come over here and they are going to break in. Okay, here they broke out, break away, and here they are breaking in. After breaking in, one of the branches will move to 0, one of them would go to infinity along the asymptote of 0 degree. So this becomes very clear from here that there are many hints that you have to get from the root locus. Many hints are there. If there are two poles, there has to be a breakaway point. If they both of them have one of the zeros is lying in the right of the S-plane, definitely they'll have a crossover point so that the branches could terminate at 0. The root locus has to be symmetric also. Then the asymptote is also along the positive real axis. That means the other uh, branch from the other closed loop pole also has to move in that direction, and it has to go along the positive real axis. Now two branches are coming together on positive real axis, and from calculations we also got a breakaway point. So there is a breakaway point at which both these branches would meet and they would move in the opposite direction. One would go along the asymptote and one would move to the 0. Okay, so there is some intuition that you have to keep on developing as you move with every step. So your question is the value of k at which at the crossover point is 4. We derived here. We got the value of k to be equal to 4, and the crossover point is really easy. There is no real there is no real value. It is just the imaginary value. Take the characteristic equation, put the value of s to be j omega. You get the value. You get the equations in the form of k and omega, and you just have to solve them for some value of omega which satisfies k. I mean the range of k. If it is greater than 0, then it has to be greater than 0. In this case, if you had got k to be less than 0, that means that there is no crossover point. And it would happen for the other cases when there are actually no crossover points. Since there was a point here, you got the value of k to be in that range. Okay. Okay. So what happened here? At this point, this is k equal to 4, this is k equal to 4. It started from here, k is equal to 0. It came here to k equal to 4. K is infinity for this branch, and k is here infinity for this branch. Okay, I'll just change the color of my pen. So the root locus starts from here at k is equal to 0. It moves here, k is equal to 4. It crosses the imaginary axis, moves to the other side. Here also same thing happens, and here is the break-in point. One of them breaks away to the pole and one of them goes along the asymptote. Here is k is equal to infinity for this branch, and here is k is equal to infinity for this branch. Okay, now so the closed loop system of problem 7 is stable for all positive. We want to just know for what value of k it is stable. Okay, so it is stable for k less than 4, because for k less than 4 only we are in this region. As soon as k is equal to 4, we move to the right half of the S-plane and the system becomes unstable. So from here we come to know that the system is stable for k less than 4. Okay, if I show the root locus, this root locus is actually not completely correct. It should be in this way. It is coming from this pole, it is moving here. Ignore this line is wrong. Okay, it moves along this. Here is k is equal to 4 at 3.32 j. This is minus 3.32 j, and it moves forward. It comes here, it breaks in here and goes along the asymptote. Similarly, from here it comes over here, it breaks away, breaks in and goes towards this point. This is k equal to infinity, this is also k is equal to infinity. So this is the complete root locus. If you have any questions, you can ask. Else we are done for today's lecture.
Okay, thank you.